morning, friends, participants in the studio and at remote centers. I welcome you on the last day of our 5-day program on recent trends in automobile engineering. So as you are aware, today we have a session on after treatment technologies to meet BS4 emission standards. Now, emissions are very important, as you have learned during the last 4 days. And primarily, the whole technical innovations that are going into engines are to meet the emission standards. And there are many techniques such as after treatment technologies which can help in meeting the emission standards. So today we have Dr. G.K. Sharma with us, who will talk on these technologies. Dr. G.K. Sharma has a very illustrious career. He is basically a mechanical engineer, PhD from IIT Delhi, and postdoctoral research in the Institute of Combustion Engineering, Germany. He has served as Director, CIRT Pune, that is Central Institute of Road Transport, and thereafter he was Director Technical in National Automotive Testing Research Implementation Program. Now, this was a very important assignment during which he set up many testing institutes, notably ARAI Pune and ICAT Delhi. So we are thankful, Dr. Sharma, that he has spared his time and come here, because these days he is working as an automotive consultant and he is very busy. So despite his busy schedule, he agreed to our request and has come here today to interact with you and share his knowledge and experience. So I welcome Dr. Sharma and request him to please.
Thank you, Professor Dhami. Good morning. I need to talk today on some of the innovations in exhaust after treatment, which will take our current engines. So this is how we are to take forward this program. As you know, Government of India has declared that in year 2020, we will have all vehicles newly manufactured to Euro 6 emission levels. Now, as Professor Dhami said, that air pollution, air qualities, these are very important. And as everybody knows, the health implications of air quality are very well established now. There's a lot of research being done. And let's talk about a diesel vehicle. For example, 10 years back, there was growth of diesel vehicles in the passenger car segment going very high. More than 60% vehicles in Germany and Europe were being built on the diesel engines. Because diesel engine, as you know, is very efficient in terms of fuel economy. And therefore, since there was a shortage of petroleum fuels in 70s and the oil crisis afterwards, OEMs or the original equipment manufacturers, the car manufacturers, started building more fuel efficient cars. And therefore the diesel got the preference. Diesel is known to have particulate emissions more than the CNG or the petrol cars. Of course, the diesel particulate matter is also considered to be carcinogenic. There is a research which suggests that the particulate matter coming around diesel is carcinogenic. There are counter views saying that it is the number which is also important. And the CNG also produces as large number of small particles, the nanoparticles, as diesel cars manufacture. So I'm not going to talk about that controversy because there are lobbies around. Somebody who makes diesel cars tells a different story. Somebody who makes a CNG or petrol car makes a different story. But all said and done, there is a carcinogenic impact or the effect seen with diesel particulate matters. So In the context of diesel vehicles, the particulate is one, the NOx is another, which is to be controlled, because the NOx is related to the ozone levels in the air quality. And the ozone levels, as you know, in the upper atmosphere, they're desirable because they, stop the ultraviolet rays to harm our skin and things like that. But at the ground level, they are not desirable. They give, that burning sensation in the eyes which you get is because of the ozone present at the ground level, and which is related to the NOx. So this is the whole scenario of vehicle related emissions, which gets into poor air quality. Air quality in a city or in a transport system is also not totally driven by the poor quality of vehicles or the poor quality of fuels. It also comes from other sources like the industrial plants, the dust in the road. We don't have the pavements which are all concrete pavements. We have a lot of mud around. So when the vehicle moves on, the dust is thrown, which is also a very nano size particles dust. So all this put together, deteriorates the air quality. But since we are on topic of automotive engines, so let us restrict ourselves to the areas where we can contribute. Probably as a civil engineer, somebody will contribute more on the managing dust in the construction sites or managing dust on the roadsides. But we as engineer and the mechanical engineers will concentrate ourselves onto how to reduce the pollution from the vehicles. Now, as I mentioned, that since air quality was concerned for the country, and we have been following US and Europe emission regulations with a gap of around 4 or 5 years. For example, if something comes in Europe in 2010, India will think about in 2015 or 14. So that's all has been going on since Euro 1 days. We have first regulation in 1999 coming up for our control of emissions in this country. Then we moved on. Then in 2010 we had a BS4 introduction. And 2017, whole country will become, from April 2017, whole country will become Euro 4. That is how this will be planned by the government. The fuel quality was major concern, because if you cannot bring a fuel with low sulfur fuel, you can't have good technologies in the after treatment. So Ministry of Petroleum worked on it, and then in 2017 all India can be supplied it with 10 ppm of sulfur fuel. So the new technology of engines and new technology after treatments can come. Then we realized that we are still 4 or 5 years behind the European scenario. So the normal going up was that we came from Euro 3 or BS3 to Euro 4, BS4. Then we could have gone to BS5 and then to BS6. But then government said this is too slow a pace for this country of our size. And our health issues and air pollution is really becoming bad. So they leapfrogged to BS6. So we decided that in 2017, whole country will be on BS4, the new production of vehicles. Of course, there will be still a lot of old vehicles which will continue. But then in 2020, we should not bring BS5, which would have been our normal, business as usual scenario. So the government decided to leapfrog it to BS6. Now we have to understand what, in terms of BS6 and BS4, what it basically means. So it is the emission levels which we will be discussing here. So my talk is more on to the heavy duty segment, as trucks and buses, because it's a big subject. So I have taken up only that small area which contributes the maximum to the pollution. Let's go to the next slide then. So in this program, I'll talk about what is the emission control strategies for BS6, what are the likely solutions seen internationally. India is yet to implement them in 2020, but our preparation is going on. Then there are two major issues, as I said, is the NOx control and the PM control. So what we can do here, and what are the type of innovations in these technologies. Because once in India, we are implementing 2020, the world has already implemented that. The US has implemented, the Europe hasn't implemented. So we have some choices available. So what can be the right choice for us? This is what we have to, focus on it. Then some of the innovative solutions where I'm involved and I feel they are good for the country. I'll be speaking about some of them. One thing is very clear, that in any strategy to control, we have to control both NOx and PM. In the engine combustion, inside an IC engine combustion, they have a trade-off in the sense if NOx goes up, the PM reduces. You can have technologies to improve PM, the NOx goes out of hand. So this simultaneously reduction of NOx and PM, which is the aim in going from Euro 3 to Euro 4 level, Euro 4 to Euro 6 level, this simultaneous reduction NOx poses problem and challenges to us. Of course, there are few technologies like, fuel emulsion. Last year, in the same forum, I talked about some of the technologies which can reduce both NOx and PM together. So we talked about water and diesel emulsions, which can bring down the peak combustion temperatures down, and you can improve this. But let us say that traditionally an engine with the normal fuel will have both NOx and PM going against each other. If you try to control one, the other goes up, or the vice versa. So we need to handle it in the after treatment systems. And how do we do? The another thing is, which makes India different, or every country different, is the type of engines you produce, the type of maintenance practices you follow in a country, the type of driving cycles you follow, because the congestion in different countries, in different parts of the world, in different cities, even in different cities in India is different. So there are challenges and opportunities which I will call them local. So it is not necessary that what is being good for the US system is equally good for Indian applications. Maybe some sort of tuning will be required in any case. So just to give you an overview of in terms of values, so when I say that we go from Euro 3 or BS3, say the words are same. The regulations we follow are similar, except some minor changes here and there. So for all discussions in my slides, Euro 3 means Euro BS6, or Euro 5 means BS5, which is not happening. Euro 6 is BS6. So basically you have a reduction in the NOx levels from Euro 3 to Euro 6 levels, which is grams per kilowatt hour in terms of a big engine, because they are done on the engine dynamometer testing. Then there's a particulate matter, which is many times reduced. Then first time in Euro 6 or the BS6, we have a number called particulate number, which is 8 into 10 raised to power 11. So small sizes of particles, so many numbers, these have to be controlled. We can't allow more than this to go. And this regulation becomes very, very critical from that point of view. So far as you notice, in all the till Euro 5, there was only limit on the NOx quantity and the PM quantity, but not on the particulate number. It only appeared in Euro 6. Because in this intervening period, there has been a lot of research which suggests that particulate matter is carcinogenic. So we need to reduce both PM and NOx drastically to move beyond Euro 3. Euro 6 also comes with PM, which necessitates DPF. I think before I move further into the program, I'd like to introduce few of the terminologies here, which we will be referring in the next slides. There are few technologies which are PM related, that is the reduced particulate matter. For example, DOC, the diesel oxidation catalyst. There's a partial oxidation catalyst which is called POC. Then there's a diesel particulate filter, and there's a new innovative technology which is called cooled particulate regeneration. Because when you have a diesel particulate filter, what happens is filter absorbs the carbon soot onto it and sends the clean exhaust out. But then with the time, the filter gets choked, which creates back pressures. So you need to regenerate it. So there are technologies for regeneration on DPF, which we'll be talking. Then there's a NOx related technologies like EGR, exhaust gas recirculation, which is an internal management to reduce peak temperatures in the system so that the NOx comes down. Then there's the SCR, which is based on urea injection or other technologies. Then there are, once you have a urea in the system, urea converts to ammonia, and ammonia does the reduction part. But then ammonia slips also. If you have more of urea, then ammonia comes out. And you can't allow more ammonia to go to the atmosphere because it's also toxic. Euro 6, for example, BS4 has a limit of 20 ppm maximum, which ammonia can escape. Similarly, in Euro 6, you have a limit of 10 ppm only. So these are the type of catalysts which you'll be using in the system. So I said that challenges and opportunities are local in BS6 and its equivalent. So if you look at Europe, there have been long time now that Euro 6 has been there for last 4 or 5 years. So the first generation vehicles which came as the Euro 6, they were basically having solutions like DPF, DOC, DPF, SCR, and ammonia slip catalyst. And SCR was a particular type. It was a copper zeolite which was sulfur intolerant. So they could introduce the sulfur low levels, so they can bring this, and they could live with copper zeolite. So heavy duty manufacturers then revisited, but there was a problem. The solution which came up first in Europe, they were giving penalty to the fuel penalty to the engine. It means in regenerating DPFs, they were burning more of fuel to get to the high temperatures where they can regenerate the DPF. They can burn the carbon from the DPF and bring down the back pressure. And therefore, since temperatures were going out of control, they needed a catalyst which can survive, and that was the copper zeolite catalyst. But then they started relooking at the other options of being less expensive in terms of cost of the catalyst, in terms of the fuel penalty on the engines. So they came with the new generation, which is generation 2 of Euro 6 vehicles, which is more based on vanadium SCRs. And vanadium SCR is also sulfur tolerant. So if you have some mix up of Euro 4 fuels with Euro 6 fuels, or some adulteration which can happen in this country to some extent, the vanadium seems to be a good choice. In China, for example, they have already introduced in Beijing and some part of China the Euro 6, and rest of the part will come through. Brazil, we are hearing that in Euro 6 will come in 2022. So we are ahead of many countries in that sense. That Euro 4 implemented with 2017, all vehicles will be Euro 4, BS4. And they are basically what we have seen in this country so far. They use an internal EGR to bring down NOx of the vehicle. Then they have a diesel oxidation catalyst. Then they have particulate filter solutions. They have some SCR experience, the ammonia-based, urea-based SCR experience, limited to city buses. As I said to you, we have skipped Euro 6, Euro 5 and jumped directly from Euro 4 to Euro 6. So there are issues in after treatment development because we have now handled the catalysts which were more into the Euro 5 solutions. We could have gradually moved on to Euro 6, but anyway, this is the government decision. So OEMs are trying for it. We as consultants are trying to help them out. The another problem which India faces is that the international solutions if we bring to give us Euro 6 solution, we have a very low speed driving condition, which does not allow the exhaust temperatures to be high enough where catalyst can work. Urea to operate, to bring to hydrolyze to ammonia, where the reduction takes place, needs at least 180 to 200 degrees centigrade temperature in the exhaust. But in a city driving cycles, you can be lower than this. So these are very critical challenges. And that's why I said our challenges are very local. You can bring the best of the technology from abroad. But if you cannot manage the temperature profile here, you have to do some innovations about it. either do some thermal insulations or waste some fuel, raise the temperature artificially, and do some of that management before the catalyst can reduce the NOx and PM. So cost is always an issue in India. So I don't think anybody will accept a Euro 6 truck or bus which is consuming more fuel than Euro 4 buses. So we have to be very innovative in this thought. Then is there a solution which can work with high sulfur fuel? Say we will in India, though we say that we are bringing all over India the same fuel, but as you know, Eastern refineries don't come up. They are old, 100-year-old refineries, and there's no point in upgrading them. Either they have to be scrapped in time, and then a new refinery is to be built up where you can bring 50 ppm or 10 ppm sulfur. So there are issues. So some part of country will still continue to have low sulfur, high sulfur fuels. And then there is a adulteration in our country, which is, I think government tries to control it. I have been part of oil company in my career. So I know how much effort the oil company does, but there is still some black sheeps in the system. And then you can have some sort of adulteration going on in some remote locations. But once the truck or bus goes there, the catalyst system will get affected. So we have to think about all those issues. Then in US, I think the focus has gone on more to N2O, which is considered a greenhouse gas. So they have moved into, then internationally the emissions are playing a big role in policy making in those countries, and then we follow that trend. So I think what is happening today in the US, 5 years later, once we have handled our BS6 solutions, we will also have to focus ourselves onto the N2 and those issues. Okay. Now, whether you call it Euro 6 in Europe or US EPA 2010 or BS6, they are almost similar emission levels. So what is that industry is doing today? The well-established OEMs are following option 1 and option 2. Option 1 is more or less the generation 1 Euro 6 engines, which practically everybody had. So what they did, they had a diesel oxidation catalyst and put lot of platinum into it so that they can manage, reducing HC and, generating, control of the things and raising temperatures for the systems afterwards. Then they have a DPF which was catalyzed. Catalyzed DPF helps to, if you put a non-catalyzed DPF, the carbon soot burns over 600 degrees C or so. So you have to raise that much temperature. But if you put a catalyzed DPF, the catalyst layer helps reducing the soot burning temperatures to around 350 degrees C. So you can work still at lower temperatures. Then, as I said, since the temperatures were raised artificially to clean up diesel particle filters, they went for zeolite based SCR systems. See, SCR is basically for NOx reduction. And then once they went into that, they have to put an ammonium slip catalyst, because more urea, if it gets into it, it harms, it comes out into exhaust and is toxic. So this was a traditional generation 1 Euro 6 engines, which happened, or even in the US the system went through. As I said, there were few issues in it. One was that how to reach the temperature, high temperature where things can be, where the carbon can be burnt out. So, and then the cost was going up because you have very high loading of platinum group metals, platinum, palladium especially. So the European industry, prominent among them the Scania and the MAN, they started working on Euro 2 solutions, Euro generation 2, which we call as Euro 6 solutions. So what they did was, they thought the cheap SCR catalyst is vanadium catalyst. And vanadium is also sulfur tolerant to an extent. But the worst part of it is that if the temperature goes above 550 degrees C, the vanadium attrition takes place. So the stability of the catalyst gets affected, and vanadium comes out into the exhaust. And those vanadium particles can still be harmful to health. So how do we manage keeping vanadium catalyst in the system? Is the only way is to keep the combustion temperatures or the exhaust temperatures lower than 550. But if you keep the temperatures lower than 550, how do you generate DPF? How do you regenerate DPF? That means how do you burn carbon onto the DPF? So then there's a whole philosophy of low temperature generation, regeneration of catalyst came up, and that makes the generation 2 catalyst. Scania has been the forerunner for this technology, and they are the most fuel efficient engines in Europe. Actually, they are the most efficient engines in the world today in Euro 6. Not only in terms of reducing the fuel consumption, but also in terms of reducing the urea consumption. Because when you come to Euro 6, the fuel economy takes a new meaning. It is a fluid economy. There's a urea fluid which is used, and there is a fuel which is used. So an engine is evaluated in terms of both the fuel consumption, and then they are declared fuel efficient. We will also face all this problem in this country in years to come. Then the next logical thinking in the process is, can I manage without putting additional heat into the system? Because as I said, the exhaust temperatures at times can go as low as 150, 180 degrees C in the city driving conditions. I was to raise them to 750 or around 700 into the generation 4 first. Into the generation 2 Euro 6 engine, I was still to manage it to 550. But is there a way that I need not put any additional fuel? Actually, there are philosophies of putting 7th injector outside the engine into the exhaust, where the fuel is deliberately burnt to raise the temperatures, or there is a post-injection within the combustion cycle, but that post-injection fuel main purpose is to raise the temperature. It doesn't deliver you the power which the main combustion delivers. So if you have to manage the temperatures within, why not I take an approach, or I think about innovatively to look at, can I generate DPF, or can I regenerate DPF, or burn its carbon, or do something with its carbon which comes on it to clean it up without raising the engine temperatures. So this is what the innovation has. There are few patents in this area. I'll be talking about one of those. And there's a company in US, they call it IVHCO, which is doing some pioneer work. So I thought I'll share that with you today. So option 3 is, they call it a CPR technology, cool particle regeneration technology, which is based on pressure pulse regeneration. The option 1 and option 2 were still the fuel based burning, raising temperatures, and then burn the diesel particulates which are absorbed by the DPF. But here is a technology which says that you can regenerate DPF by putting a pressure pulse wave. So the logic is very simple. It dislodges soot. It does not incineration. It does not do incineration. It doesn't burn. So the logic is that the exhaust stream came with lot of soot particles, came to the DPF, the filter, and get absorbed because of the exhaust energy impact. Is there a way I can de-impact it, or I can dislodge it from the system? So that is how this patent research has done. So the few more slides which I'll continue here. I will be using data from 2 companies here, and therefore I want to acknowledge that. The thermal management and low temperatures pulse regeneration is courtesy of a Helda Topsoe, Denmark. I have taken some slides from them. And I I had privy to this information because I worked as consultant to Haldat also for the Denmark company. And then there is a some data which I using from cool particulate regeneration. This is courtesy IVH, so Indus Valley Holding Corporation, USA. We have a collaboration agreement with this company. Like I'm part of a company, small group, private limited company, and we have a collaboration with them. So that data I'll be using. So as I said in the beginning, there are two aspects. One is reducing PM and reducing NOx. Now reducing PM needs temperatures to be raised to burn it. This is the conventional wisdom. I'm talking about the conventional existing systems. So you raise temperatures, but if you raise too much, you get into the copper zeolite or iron zeolite catalyst because they can survive high temperature. But if you can manage your reburning of the DPF within minimum temperature ranges, you can have a choice of a different SCR, which is vanadium based. So this few slides are about this. So what when we go to the BS6, as I said, in BS4 we had very limited experience of ammonia SCR. I think there are only 2,000 to 3,000 buses on all India basis which are currently using this, because the government has not created a urea infrastructure as such. There are talks going on. There are private players like Gulf Oil Company and some NPL. They do supply urea if you demand from them. So there's a some bus transports which have worked it out. So one is that cost is always an issue in India. So we must be looking for a SCR which is low cost. We must look for a technology which reduces both fuel and urea consumption. Most likely in BS6 our fuel economy will go down if you put all these things together, because there will be urea consumption and there will also be issue on maintaining some temperature levels. So I believe that a BS3 engine may be more fuel efficient in terms of, but bad on emissions, while Euro 6 will be good in emissions and slightly inferior in the fuel consumption, probably, or a urea plus fuel put together. And then another thing is, we want high NOx conversion because our engines are producing a lot of NOx today, but we also want it at low speed operation, which is very critical of India. Say in a city like Bangalore, the average vehicle speed has come down to 12 to 15 kilometers per hour. I think we are not advancing. That city is advancing in IT, but going to bullock cart speed in the vehicle. So there's something which is very peculiar of Indian cities. So how do we do maximum NOx conversion at low speed, low temperatures? Then our engines traditionally have been oil consumption, high oil consumption engines compared to US and Europe. I won't blame anybody around that, but I think the overall, to bring down, keep the cost low on the vehicle, we cut some corners, and that is where we'll end up in poor metallurgy and things like that. But it is improving. Not to say that we are stagnant in that, we are improving on oil consumption. Then there is a possibility of wrong ash going into. So there are lubricants which have different ash levels. Up to Euro 4, ash level is not an issue. But in Euro 6, when DPF comes up, you can burn carbon which comes from DPF, but you can't burn ash. They get deposited. They have to be condemned actually after some time. The DPFs have to be condemned. So, and now you have a vehicle in India which is tractor, which is under no control of emissions, or a DG set using a lubricant. And the truck or bus guy finds that oil is cheaper available. So he puts that oil into the engine which is designed for Euro 6 by mistake. Then all this can land you up in problem in Euro 6. Then tolerant to sulfur is in fuel desirable. Although the government says will bring 10 ppm sulfur in 2020. Actually, it will be available in 2019 for validation test with OEMs. But all said and done, some adulteration, given our society structure, Some adulteration may happen here and there, but once an adulterated fuel goes in, and if you have a copper zeolite or something, it really gets problem. So I have taken this slide from Halda Topsoe, as I said. There is a possibility if we use latest generation vanadium SCR, you can have over 190%, you can have over 90% conversion at 180 degrees C with 50% NO2. These are more technical data, but I'm just trying to give this an overview that the temperatures which are going to be minimum required to be raised is 180 degree. And if you want more conversion from the engine of NOx, then you have to raise it to higher temperatures. That means to come to Euro 6 level, your starting NOx also you have to control. Say if you have some EGR, some SCR, these combinations can work better in terms of percentage of NOx conversion reduction possibilities. And there will always be an issue that you can pass an ARI test, but what happens to low speed driving, low real world driving emissions? And then how do you get to NO2 of that level? That's another issue. So NOx does not produce, the exhaust does not produce this much of NOx level, NO2 level. It produces NOx, but within NOx, NO2 is not so high, which is needed for conversions. So this NO2 is generated by DOC. Therefore, DOC, diesel oxidation catalyst, is almost part of any modern system. DOC helps reduce, though they call it diesel oxidation catalyst, it helps reduce hydrocarbons overall. Some part of particulate matter, which is known as oil soluble fraction, SOFs they call it, that can be burnt in DOC. The hard soot carbon cannot be burnt in DOC. It has to be brought to the DPF, captured there, burnt. That is how it has to be. So traditionally, this is what a typical after exhaust system train will look. You have a vehicle which produces exhaust. You can manipulate exhaust to some extent. For example, you can have a EGR. You can have a starting NOx of 6, or you can have a starting NOx of 12 grams per kilowatt hour, depending on the engine. Some people use both combination, like MAN in Germany uses both EGR and SCR systems for bringing NOx. Scania favors doing all known EGR, all NOx, high level NOx, and then reduce them in SCR. So you have a diesel oxidation catalyst, you have a catalyzed DPF, then you have an SCR and SC. There is a diesel being put into the exhaust system. This is basically for raising the temperature of the exhaust systems. And then urea is again, as I said, to produce ammonia to reduction in the gases. So this combination where you use vanadium is very attractive for Indian context, I believe. One is they are low cost SCRs. They can work with low system PGM, the platinum group metals. Then it affords high conversion ratios of NOx at low temperatures and can be used with and without EGR, and moreover sulfur tolerant to a great extent. So the base oils, the lubricant, the sulfur need not be controlled. The mix up it can handle if somewhere it happens. A kerosene gets mixed up with diesel, then it can handle. So vanadium seems to be a good choice for country. But still, there will be biggest issue there. How do we manage DPF regeneration to protect SCR wash coat? That is, the temperature going to the SCR block, brick, if I call them brick, the temperature of exhaust going to SCR should not exceed 500 or 550 degrees C. So this is what the management of DPF generation will take us to the second part of the talk. Of course, there is service. I have talked about this sulfur tolerance of SCR catalyst. See, what happens is, vanadium catalyst is a very good in handling sulfur. That's why they call it sulfur tolerant. It becomes inactive, no doubt. Sulfur gets into the pore sites, and slowly the activity goes down, as you're saying, on this time frame. But the moment you raise its temperature, it deactivates. Oh, sorry, the sulfur get activated again. The SCR gets activated, and then you achieve the same level of convergence. So there will be some drop in the activity. The moment the temperatures goes up, it recovers its activity. So therefore, we call it a sulfur tolerant. It is not that sulfur doesn't affect it, sulfur affects it, but much less than in copper geolite systems, number one. Sulfur is also poison to DOCs, so we also need to have that issue, that sulfur, reduced sulfur is always better. Deactivation caused by pore plugging of ammonium bisulfate. This deactivation is reversible. With ultra low sulfur fill, the issue is minimal. So this is what I said, that when the temperature goes up, it can be activated. Geolites are also, copper geolites are also sensitive to ammonium bisulfate. For copper geolites, sulfur also reacts with copper and forms copper sulfate. Needs high temperature to be regenerated. Therefore, you have to go to 700 plus, as you said, the generation 1 Euro 6 solutions in Europe. I talked about copper geolites. And even very low sulfur fuel leads to a noticeable deactivation over time. And therefore, regeneration is necessary. So frequently, you will find that the 7th injector or the exhaust injector in the exhaust, which I showed in the previous slide, that has to be operated more often with the copper geolite solutions. So what is key message in SCR for NOx control? Vanadium technology is cost effective. There has been trend of more vanadium in Europe. Goes with it the lower cost of both catalyst and PGM used in system. So you can have DOC with low PGM, you can have DPFs catalyzed with low PGM, platinum and palladium. Sulfur tolerant, high conversion and low temperature. These are important to us to Indian context. That's why I'm highlighting them. And then it's futuristic as well. See, I said no, in US, the focus is now, they've already controlled emissions to Euro 6 and that level, EPA 2013 levels. Then they are talking about greenhouse gases. And now they have found out, so far the focus was on CO2 from the exhaust. They say now N2O is more reactive in the categories of greenhouse gases. So they want to control N2O. So if you look at that future trends, obviously in India that will also follow into after 2020, maybe 2025 or 23, you will have government talking about N2 or things like that. So why not to capture it right now? So vanadium is good in that. I have a lot of slides on this, which I thought they are not needed here for the moment, but just to leave a thought process here that this is a futuristic technology which will take care of newer emissions. Then the hurdle was so far that SCR has to be maintained below 550 degrees C. Can we do the DPF regeneration? So this can be managed without exceeding 500. Then, as I said, what is the innovation then? Innovation is that I can even use non-thermal DPF regeneration technology, which is most suitable for Indian driving. Both CPR and DPF is sulfur tolerant. So these are the positive points of a type of SCR combination, the DPF combination we are talking for this country. And then how do we manage the regeneration? That will still be an issue because we have had no experience. Actually, when the government says that you have collaborations, you are exporting vehicles and you have collaborations from abroad, you can bring new technologies. They probably fail to notice that our driving conditions are very difficult. And say it's fine to have an legislation, but and OEMs will also meet on the ARI test beds and things like that. But when it goes to field, what happens to if the DPF does not get regenerated? What people will do? What is our experience of CNG city buses in Delhi? The three-way catalyst guys removed because it was not functioning, or it was creating some back pressure issues. So NOx from CNG buses went up. Similarly, here you'll drive in. The new bus will come from factory, well certified by ARI and other institutions, meeting all Euro 6 specifications. After 500,000 kilometers, the DPF will stop regenerating because our low temperatures are in the country, and people will remove DPF, will have ordinary silencers. So we will not achieve what we want to achieve. So the choice of technology is very important, and that is what I have been emphasizing in various forums, that we need to talk about what is practical for India.
One question.
Yeah.
Previous slide.
Okay.
And you also said right now that we have low temperatures there. What does that mean?
Say when the vehicle runs on the city driving, okay, in the city driving, traditionally you don't run at that high speeds and things like that. Okay, so there is the exhaust temperatures which come which have been profiled. They are not more than 180 or so. There will be some peaks going up, but most of the time it is lower than that. And urea in SCR system cannot hydrolyze below 180 degrees C temperature in the exhaust. So exhaust has to be brought before that, before SCR becomes effective. So this is what I mean by low temperature in driving conditions. There is another argument which people say, that our city buses are overloaded. So you are overloaded, so you must be putting a lot of throttle, and then they will raise temperature. But all the data which I have seen, even on the overloaded buses, because the speed is so low, the temperature of the exhaust is not going up. So you will have difficulties in regenerating DPF, you will have difficulties in hydrolyzing urea to control NOx. This is what it means.
The engine must run at higher RPM to...
Yeah, it has to have that. Or alternatively, what people do is, there are various ways of raising temperatures in the exhaust. Some people have even tried, there are some patents, but what they do is, they do sort of regenerative braking, okay, which is part of hybrid buses or part of electric buses. So that regenerative, they don't store in the battery, but they give it to a resistive, element, and it heats up. That's one way. Then people do throttle. They put exhaust throttle. When the engine was idling, or it's on a, for example, on a red light standing there, cross, they just put the exhaust throttle. Engine doesn't die. They don't put that much of exhaust throttle. Engine doesn't die, but it raises temperatures because the flow has been restricted. Okay, because ultimately it is the flow which throws it out. And in the idling and lower RPMs, the more air, it's a diesel engine, as you know, the combustion is high air fuel ratios. So if turbocharger is still pushing a lot of air, and the idling, the fuel is not there, then obviously the temperatures come down. Yeah, please.
I have a doubt, not a question. I just want to clear that when NOx is produced from SCR is used to produce NOx.
True.
And DPF, diesel particulate
Filter.
particulate filter. That is absorbing only particulate matter.
Yes.
That is dissolving fuel.
That is into the exhaust. That is generated in
It's coming
exhaust.
from the fuel.
No, fuel burns into the combustion chamber. Then both NOx and PM are produced, like hydrocarbons are produced, CO is produced.
Very soil, PM is on the-
Yes,
That is basically a particle in the gas.
yes.
That's not. And at low speed, more NOx is produced.
NOx is a function of temperature in the exhaust system. No, sorry, combustion temperature in the in cylinder temperature.
That is also function of speed.
That need not be. That need not be. Combustion will always produce a particular temperatures in the combustion chamber. So what happens is exhaust, once it comes out of the combustion chamber, then the type of air flow and the way it is exhausted out, it helps in varying the ratios. But within the temperature, within the system, if you maintain the same temperatures, it will produce similar level of NOx. If you maintain high temperatures, it will produce high NOx. If you maintain low temperatures, no NOx. Therefore, EGR has come in, exhaust gas recirculation. What it does, it takes some of the exhaust gases, puts it back into the engine, so that the reactive part of the air-fuel mixture is reduced. Okay, that's how the NOx levels come down, because the temperatures then comes down because of the inactive material within the combustion chamber. Any other question? Can we move on? Or if your audience from the satellite centers or something like that?
So far, if there is any question.
Is there any question from any center? Please ask.
Because then we will move to DPF regeneration. So this was up to NOx. Okay. If not, then we move on to the next part of the lecture. So I have given a fair idea about NOx control, SCR technology, and also I raised the question that the choice of SCR will depend on what type of DPF regeneration you want to aim. Okay, if you are forced to take a very high temperature philosophy of regeneration, then you will have choice to go beyond SCR. You have to go to copper zeolite or iron zeolite or that, which can withstand the high temperatures. But then in an Indian condition where temperatures are already low, 180 or 170 degrees C, for example, an average temperature if I'm talking about, or even lower, then to take it to 550 or beyond that will need lot of fuel penalty. It means from somewhere outside you have to bring that temperature rise. Engine is not producing itself. So either you will have a strategy in the engine ECU to have a post injection, so that after the combustion power is delivered, you leave some fuel extra which keeps burning and raising temperatures. Or you have a 7th injector, we call it extra injector, is called 7th because most of the engines are 6 cylinders, so they will call it 7th, but in the 4 cylinder it will be 5th injector. So that means the extra injector has to be driven. Now this is what the conventional wisdom is for DPF regeneration. And then we'll talk about what is innovation in it. Say like I said that there is an innovation in DPF regeneration within the conventional. To make SCR, Vanadium SCR possible, there was a lot of innovation in DPF regeneration strategy, which became generation 2 of Euro 6 in Europe. Similarly, for India, I think there is a chance or there is an opportunity to look at different options, which we'll be covering in the second part of this presentation after I covered the conventional. So what is DPF regeneration? Something which gets choked has to be removed. That's the regeneration. The carbon particles have choked the filter. They have to be removed. So soot built up in the DPF is highly dependent on the uses. One is that amount of time is spent at high and low temperatures. It is not like this, that the engine is started and all the soot comes and it gets absorbed and absorbed forever. No, it's a dynamic process. Sometimes engine will be running at high temperatures, sometimes at low temperatures, medium temperatures. So some partial burning of carbon soot from the DPF filter will always happen. But with time, over time, there will be a lot of non-regenerative. The carbon which gets built up, which will not burn, which will get into the pores and the temperature doesn't rise to that level, so it will remain there. And then, as I said, carbon can be burnt two ways. One is, when we say temperature rising, is one part of the story. For anything to burn, what you need is temperature, or the flash which you used to call. And you also need some sort of oxygen. Otherwise, carbon will not burn, fuel will not burn. If you put petrol in this bottle and put a matchstick here, it will not burn, I'm so sure. But if you put a matchstick, the whole room will be burnt. So it's a proper air-fuel ratio where it burns. So carbon in the soot, carbon or the soot in the DPF will only burn if you have high temperatures and if you have oxygen available. Now, this oxygen available is not in the terms of oxygen sometimes. It is also can come from NO2, from some dissociation of gases, and then NO2 acts into the, helps into the burning of carbon in the particle. This NO2 is package of the NOx, but very little. So this also has to be raised. DOC does that part. The diesel oxidation catalyst, that's why it was oxidation. It will convert NO to NO2, and that NO2 participates in DPF regeneration. So this is conventional DPF regeneration. That is, they call it passive or they call it active. And there is a third category which is now known as active passive. I'll explain that to you later. But conventionally, these are two, passive, which is NO2 driven. If you keep the temperature, low temperature regeneration of the DPF, that is, if you do not, what should I say, do not deliberately add extra fuel into the system to burn DPF, to burn catalyst, burn carbon, that is called as passive, which is most of NO2 driven. But there is an active regeneration. Passive is when engine is running, it produces some NO2 or use some, increase NO2 by DOC, and then the DPF gets cleaned. This is passive regeneration. But if it fails, you're not raising enough temperatures, you're not producing enough NO2. If it fails, then what do? You put extra fuel onto the DOC, which is fuel dosing. That is 7th injector. And that is O2 driven. The moment you put fuel onto the DOC, the NO2 part reduces, which was the natural phenomena happening in the DOC. Now you deliberately put fuel, so deliberately you will have a lot of oxygen around because air fuel comes in, and then that is driven the high temperature regeneration. So there are two innovative approaches. One is within the conventional, which I said active passive, which is known as pulse temperature driven low temperature region. So what you do is, if you put all the time continuous flow of fuel into the exhaust, the temperature keeps going up and they reach where vanadium cannot handle it. They will go into the region where copper gyrate will be necessary, 700 plus. So what they do is, in this is the Halder-Topsoe's patented technology. What they do is, they put some fuel and allow the temperature to go up and come down again, and then after some time again put. So it's a sort of thermal pulse which they give to the catalyst. So they still raise temperatures, but not hit the peak temperature all along. So the vanadium attrition doesn't take place. This is proven technology. Anybody can adopt it. Though Haldat also had patents, but since it's a sort of process, anybody can design about his own methodology through the ECU control systems and the 7th injector or post injection work it.
This happens in the exhaust part. Exhaust pipe.
Exhaust pipe. So this 7th injector is put into the exhaust pipe. So initially it is done like this, but then engine ECU guy can take it into the post injection also.
So if they inject the fuel, that means some combustion takes place again there.
Yeah. To raise the temperature, you have to have fire.
Yeah.
So that combustion you do internally or you do externally. Now internally you have failed to raise that much temperature. Okay. You delivered power. So some energy went into the power, some into the exhaust, some into the coolant system. Okay. Now that was not sufficient enough to raise the temperatures to the into the exhaust system to be active.
But are we talking this for say diesel engines only? Or
Diesel engines.
So because otherwise in a diesel engine it's the compression which raises the temperature.
That's it.
But in exhaust, do we have that temperature which will enable combustion by injecting fuel?
Yeah, because you have 150-60 degree centigrade temperatures anyway. So the temperature is high enough where it will run. So there is another technology which is cooled particle regeneration, which is more innovative in its nature, which is pulse pressure driven. This has only reached proto stage today. You have no commercial engine being used on this. Okay. The company IVHCO in US is demonstrating to Cummins, is demonstrating to Volkswagen and all those groups in different type of engines, generating set, this and that. But I think it is still to take its own. But it has more appeal for Indian market. That's why I am focusing on this.
Sir, this vanadium is a catalyst,
Vanadium is a catalyst, V2O5.
and we have a problem with its high temperature.
Yes.
And what kind?
V2O5 is volatile at some temperatures, or it leaves its wash coat where it is stuck up on the catalyst. Attrition takes place. So it comes out, vanadium comes out as particles themselves.
That must be-
So there is a toxic, vanadium is associated with toxic nature. So it should not be allowed to leave the DPF. So there is a very interesting US regulation. Say the development of SCR is pre-DPF. Actually, before DPF, the SCRs were developed all over the world. That's the sequence. So in US, they said SCR DPF can be used, SCR can be used, vanadium, if there's a DPF after it. Okay. So some of the old vehicles, year vehicles, they have this arrangement. The first is the SCR, then the DPF. So if there attrition takes place by mistake or by mismanagement of the fuel, then DPF doesn't allow those particles to go to the atmosphere. So only one or two, those systems were allowed in EPA systems. Today, traditionally, if you look at those pictures which I've shown, the DPF comes first, SCR later. Because DPF needs more temperature generation. So if you put it block after block, brick after brick, and the DPF is the last brick, you will never have temperature reaching that. So you have to bring it as close to possible to the exhaust manifold. This is what is needed probably. So basically, in DPF regeneration, 4 concepts exist. I think I briefly touched upon, but let me summarize them again. One is the high temperature regeneration. That means the baseline temperature is always higher than 580, or is higher than 550 actually. That is how we have started defining it. Because up to 580, 550, 580, vanadium can work. Beyond that, copper gelato has to work. So the conventional high temperature regeneration is baseline is 580. And this is based on continuous diesel dosing. that is either the post injector or the 7th injector, has to continuously put fuel to keep the temperature high. Because I said 180, 190 will be our temperatures. Their temperatures may be 250 already in some of the usages. So they will need less fuel to put. In Europe and US, we will have to put more fuel to bring the temperatures to that level. So this is high temperature regeneration. I think is not recommended for India. It's my personal view. But I'm also aware of some OEMs who want to work with copper zeolite, because they say we will ask deliberately to raise the temperatures, but we don't want any field problems. Because if the temperatures are not that adequately, the regeneration cycles are not maintained, you will have problem in DPF. So, but their views, always in technology, they are pro views and the opposite views. So primarily what I'm trying to say is that high temperature regeneration is primarily oxygen based. So we will call it active regeneration. There's a low temperature regeneration which limits SCR inlet temperature to below 500. This is the mean. This is also primarily oxygen based regeneration, continuously diesel dosing. Okay, both low temperature and high temperature, depending on the type of SCR you use, and the OEMs who can manage it, both have been in existence. They are all proven technology in generation 1 and generation 2, early stages of generation 2. In the latest stages of generation 2, that means 2015 onwards, in Europe, pulse temperature regeneration has also figuring out. So it's limits SCR inlet temperature to below 500 degrees C, like the low temperature regeneration, but it is also partially NO2 based, not all oxygen based. It means it is, I'll call it a hybrid system. So it is taking advantage of the inherent quality of the exhaust gas to produce NO2 on the DOC and let the fuel burn, let this NO2 burn particulate matter to the extent it can. Where it fails, then you give a pulse of a fuel or a temperature rise of a fuel. So this is what they call as intermittent diesel dosing. And this is what Haldar Topsoe, who specializes in this, and specializes in the vanadium catalyst actually, they have brought it about. So these three, I'll call it as proven technologies. Okay. India can adopt either of the three. My choice, if I'm given as a consultant a choice, will be the third one, the pulse temperature regeneration, which is immediately if you have to bring a solution to the market. Okay. But we still have 3 years to go. We are in 2017. If we were talking this in 2019 and 20 we were to bring it, probably that would have been my answer. But then there is a new innovative technology which people are trying. Probably the developer of the technology missed the bus in European market or the US market because the technology developed later. And they brought 2015, everybody was on Euro 5, or 2014, everybody was on Euro 5. US was actually Euro 6 in 2010 at that level. And this technology came up later. So people who have invested money in an already proven technologies and have started marketing, for them to switch over to a new technology, again needs validation and things like that and lot of effort. So they are looking at it. They are looking at it from the angle of not automotive markets, but they are also to follow some tractor regulations, some DG set regulations, some marine regulations, some railroad regulations, which will still to go the deeper or stricter as the automotive has already moved. So in Europe, in US, they are looking at it. But for India, I think this is the right time to look at it, invest money into it and validate it. And probably it gives you a very effective solution. So here what they do, as I mentioned, it's a pulse pressure generation. It's not a temperature pulse, it's pulse pressure. So like they were doing extra fuel whenever they need to raise the temperature, maintain to burn. Here he gives pressure pulse back to the system, dislodges, and when he feels his pressure back pressure is building up, which is not permissible, then he again gives a back pressure pulse, dislodges some, keeps it somewhere in some pocket. He has a container to restore back, and then keeps doing this whole life of the vehicle. Okay, so every time some part of it gets dislodged, loosens up with the exhaust back pressure, goes to a dump, and this dump can be taken out at the time of either oil change or something like that. This is his basic philosophy. I am personally very impressed because it is doable, and of course he is also trying further innovations, that can this suit be brought to the lubricant directly, so that dumping at later station need not be done, or it can be blended into the fuel, so he can reuse. So this is a part of research. It's a research group which is focusing on it. Okay, so this was low temperature regeneration. Out of that, I thought we'll share some of it. So soot can react either with NOx, oxygen, or NO2. While dosing diesel to increase the temperature, NO2 production in DOC is inhibited. That's what I told you. If we exploit NO2 production over DOC, we will help lowering the DPF regeneration temperature below 550 degrees C. That is the basic philosophy of Halder-Topsoe in making this catalyst work with the temperature pulses. So this is the type of pictorial scenario it happens. As soon as the pressure goes up, the DPF back pressure goes up, he has to operate. He has to give a pulse, raise the temperature, so it burns little bit of soot. And then little bit of soot burns, the pressure comes down, So though it's a temperature pulse given, but in schematic it is the DPF which is getting regenerated on each pulse. Okay, so on an average he maintains a temperature profile which is lower than 550. That is how he does. And at high temperature, they just take 2 grams of soot per liter of a catalyst volume, which they degenerate. They don't allow it to go beyond, say, 20-30 grams of per liter of DPF and then regenerate, like some of the high temperature guys will do. What they will do, they will allow it to accumulate, and when they reach a point where they want to, the engine will start misbehaving because back pressure has gone up. That time they will pump more fuel, burn it off. That is a traditional way of regenerating. But these guys in Denmark don't do that. Their philosophy is, every time the soot is come to the filter, very soon they raise the temperature pulse, bring it down. So continuously they keep doing. That's why they call it a pulse. So key results, what are the key results? Filter regeneration possible at low temperatures. And what is the advantage to an OEM and a user? User saves 50% on the fuel because he need not waste fuel and need not inhibit the tendency of the natural exhaust to burn soot to some level. So that is what NO2 was doing. So in the deliberate soot regeneration, you have actually killed that inherent possibilities of NO2 to generate. You are putting fuel, so DOC makes more oxygen, takes more oxygen in and burns it. And then with external acid joining or post injection managed without exceeding 500 degrees C. That's what is all about. And this also allows you to lower catalyst and PGM costs by using Vanadium SCR. Okay, in this understanding of DPF regeneration, we also have to understand the role of DOC. Okay, we have said about how to manage DPF regeneration so that survival of vanadium catalyst happens. This was the part of my process of thinking so far. Now we need to see that what is that we can do about catalyzed DPF and DOC And do we understand their functions properly before we really attempt a DPF regeneration? So DSC for low temperature systems. So there are two categories which are coming now. We have defined that SCR to survive and vanadium, we need to have a low temperature regeneration system. For copper zeolite systems to survive, we have to have a high temperature, which has positives and negatives on both sides. So DOC for low temperature system, you have PGM load, platinum group metals load, which is 10 to 20 grams per foot cube of the catalyst, which is a mix of platinum and palladium. This is considered a high level of platinum. One of the only reason to go to high temperature is to desulfurize the carrier. So DOC for high temperature systems, you have still higher PGM loading. Now SC dosing in DOC produces O2 for DPF regeneration, inhibits NO2 needed for SCR for low temperature conversions. Now this is what DOC, so you have to make a very thoughtful choice of the DOC platinum loading, what you want to do with it. Then catalyzed DPF for low temperature systems, again can work with very low PGM loading. Why you need DPF coating? Actually, that's why you call it catalyzed DPF. It is needed to reoxidize NO to NO2 in order to enhance the low temperature performance SCR catalyst. So, you are seeing the interconnections DOC to DPF, DPF to NOx. So this whole is a very complex chemistry scenario, and there have to be very delicate balances. So hypothesis which I'm coming up with, and where I think the solution lies for India, is if one can generate DPF without any heat addition and get SCR working at good conversion efficiency, then even perhaps low sulfur diesel is not needed. So Indian refineries are investing around 50,000 crores to bring a US BS6 fuel. Okay. In bringing BS3 to BS4 fuel, they have already spent around 80,000 crores in last 5 years. Now another 40 to 50,000 crores are on the table. Okay. I won't say that we should not upgrade. We should upgrade because there is advantage in it. But then there's a very social question, whether you must do this much to improve this, or you need to spend on other infrastructure in the country to feed poor or whatever. But I'm not a politician to talk about this. But I think this is more driven by our philosophy to follow others rather than thinking very locally. Now we have to have some local solutions, and probably it was not needed all along. The OEMs are also governed by their counterparts in US, like everybody has collaboration in Japan or US or Europe. So they bring technology from there, so they need some good fuel. And there is a whole complex set of things. So some independent researchers and independent thinkers like us can probably think differently because we don't belong to any block. And therefore I believe that there is a possible innovation solution, which is CPR plus vanadium SCR, and which can work, both can work with even today's current fuel levels. I have talked this slide to one of the oil companies, and everybody appreciated, but they are afraid to talk it back to the higher management or ministries, because there is commitment to government levels. So as they say, a lie told 10 times become truth. So that's the type of is happening. Somebody said it has to be done, and the other guy said it has to be done, and done, and the money is spent from there. But let us see. There are other technologies coming up. There are other vehicles for even if I forget at the moment, Euro 6, you have taken some decisions about the country, about the technologies. There is tractor industry, there is a diesel generating industry, there are other type of three-wheelers, so many other, off-road cranes, shaped railways. where we have to think a little more locally. That's what I would say.